Thank you. Okay, so I guess we're good to go. So good evening, everyone, here at Domi Station as well as online tuning in. My name is Jeremy Quinto, and today we are having a co-talk here at Domi Station, mainly about connecting AI to your software application. So without further ado, let's get started on that. But before we actually get into that, I'd like to give a little bit of some background about myself. So again, my name is Jeremy Quinto. I am a graduate student at Florida State University. I actually graduated last fall in the Department of Scientific Computing. And during my time in graduate school, I also interned and worked at USci Labs, which at the time was a machine learning startup right here at Domi Station. At the time, I mainly worked on backend API development, a little bit of front end development, and especially machine learning, AI, and model deployment testing, which will be the main talk of today. Um, as you know, machine learning has become a widespread topic as of recently within the past decade, and we, both at USci and trying to move Tallahassee as well towards that sort of development paradigm. So I'm really excited to talk about this. Um, After the 2 years of working at NewSci, Call Simulator became its own entity, which is an abstraction of what we're working at NewSci Labs. And since then, I have been working in that particular space, basically doing the same thing, deploying applications, creating, gathering data, and creating new models to actually train call center operators on how they should be receiving calls and preparing them for any sort of scenario in the call center space, whether it be extremely outrageous or a typical everyday call. But that's a little bit of background about me, and let's get into the meat of the topic. So, machine learning in the cloud is a very generalized topic in the sense that, first of all, we have to get the notion of cloud computing understood first. In a nutshell, basically, cloud computing is compute resources that are available in some remote environment in one way or the other, and you, as the user, has access to some chunk of that somewhere on the internet where you're not really sure of where that location is of how you're accessing those resources, but it's just out there in some way, shape, or form. And of course, this is a rapidly growing trend, both in development as well as in business, especially recently with the shortage of silicon, resulting in a lot of hardware being difficult to acquire. In addition to this, on the daily, new complex applications are being deployed and built on local machines. And there becomes a point in time where it just isn't profitable or worth it to have a lot of your applications hosted physically on your device, as you could be using those resources for other tasks. So you'll notice that within the past decade, a lot of businesses and users, developers have started moving a lot of their technical stack to the cloud to better keep things organized and sorted, and always having things up and running somewhere, regardless of where they are. In addition to this, cloud providers, those who host these cloud services, have made these platforms a lot more accessible within the past decade. So newcomers from all experience groups can get the most out of the services that a lot of these cloud providers give you. Um, and it's very easy to interface with, simply just using the built-in console that the platform itself This code talk is mainly about connecting your AI to the application that you're trying to interface with, and less so of the actual building of your machine learning framework. So I didn't want to get too deep into that paradigm because that could be an entire code talk in itself. So we have some basic assumptions here. The first one being that you do have some machine learning model already trained in one of these following frameworks. And here I've listed the four most common frameworks. The first being TensorFlow, scikit-learn, XGBoost, and lastly, and arguably the fastest growing machine learning framework, PyTorch. Now, for you PyTorch developers out there, it is definitely gaining in popularity ever so steadily every day. But for certain cloud providers, support is still being slowly implemented. So you'll notice that for some services, they might still be in a beta version for providing you the compatibility support for hosting PyTorch models. But later on in this presentation, we'll address some of those issues if you do ever come into those obstacles regarding deploying PyTorch specific models. From the top of my head, I do know that Amazon Web Services and recently Google Cloud Platform have both brought in support, at least at the beta version, for PyTorch. So movements are definitely being made in regards to that specific framework. And the second assumption, of course, is that you're looking to transfer this newly trained model that you have in either your local environment or in the Google Cloud Colab environment. Usually those are the two that most beginners are developing in, to the cloud for either you to experiment on or for others to experiment and utilize with as well. So you have your local model on your machine or in Google Colab, and you don't really know what to do next, except for, you got to get that to the cloud as quickly and as steadily as possible. But before you do that, there's actually some qualities of your model or considerations that you should keep in mind whenever you are developing. And I've listed 5 main points here that everyone should pretty much keep in mind or keep tabs on at all times. The number one being exactly how much memory or RAM does your model require. So testing this is pretty standard. Essentially what you want to do is you want to have a clean environment and have your already trained model just loaded in your local memory and start running predictions. Do like a few dozen or however many your task actually requires. Doing so gives you the ability to determine the minimum and the maximum memory that your model will consume when it's deployed. This is extremely helpful, especially when you start moving to the cloud environment, because having to constantly deploy and test to see if your model meets within the compute resources you allocate will remove a lot of tedium during your development. Number two is a GPU a requirement for running your model? So GPU is a graphical processing unit. If you're usually training your model, you use a GPU, but this is a different sort of scenario where you're deploying it and you're trying to get predictions about your model rather than training. So number two kinds of lines up with number 3 and 4, which is how responsive and how often will you be using your model. And of course, this can be for definitely different use cases. Maybe you just want to have your model deployed for your own use. lot more alternatives that you can choose here. But just be aware that if you decide to go to those alternatives, there might be additional costs or some considerations you need to make in those specific environments. The big three here being Google Cloud Platform, or GCP for short, Microsoft Azure Cloud Services, or ACS, and Amazon Web Services, or AWS. Specifically here at Call Simulator and at NewsSci, we here use the Google Cloud Platform. So you'll notice like a lot of the demos and a lot of UI layout here is going to be related to that cloud service. But generally, you can think of that if it's available in one cloud platform of the big three, it's going to be available in the other two as well, just with some different naming schemes, as well as some different terminologies and maybe one or two little changes in the methods of how you interact with that service. And as I mentioned before, the cloud space has been readily developing within the past decade, up to the point where machine learning in itself has become its own vertical amongst these big three cloud platforms. So for Amazon AWS, they have SageMaker Studio. For Microsoft Azure, they have the Machine Learning Studio. And for Google Cloud, they have the AI platform. And all of these are suites of tools and services that specifically are in line with user deployment of their own models, remote training of their models, and also cataloging of models. Specifically, from my experience in Google Cloud, there's a catalog available for you to see what other industries or what other developers have done to deploy their models, and you can deploy it yourself and gain some inference and some ideas of how they approach these problems, and also, gives you some sense of experimentation if you're not as experienced in developing your own models from scratch, or you're a little bit intimidated about the overwhelmingness of machine learning. So now we have some of those machine learning, some of those Google Cloud areas covered up. So now let's just start getting our model into the remote environment. So the first step you're really going to do is you're going to want to upload your model to cloud storage. What exactly is cloud storage? It's basically somewhere on the internet where you partition a specific space for you to store your specific files. Your files can be anything that you want, but for our specific case, we're going to be storing our machine learning model files. So in step one, we just create a storage bucket. It can be any name whatsoever. In the specific example, I call it the code talks bucket. And from there, I just upload the locally trained model files that I have to the remote environment. Very simple two-step process. And of course, I'm using the integrated Google Cloud interface that you can access through your web browser when you're conducting this practice. So now you have your model up in cloud storage. What exactly do you do next? I mean, it's already up there in the remote environment, so shouldn't it just be able to be deployed immediately? And the answer is yes, actually. They've really streamlined a lot of the model deployment process to just a few clicks on your browser and just making sure that a couple fields are filled in by you, the user. So for this example, we navigate to the AI platform tab where Google Cloud's own suite of machine learning services are available. We go specifically to that model tab and we simply just create a model. And creating a model is as simple as making a name for it to organize the model in a specific namespace. In this certain example, I just call it the code talks text model. And I'm using it as a regional endpoint because at the moment, we're really not expecting it for global use, just for regional displaying. More so in the case that maybe you only want to test it, or you only want people within your organization to test it, or only people within your region to test it. There's wide customization available for you as the user just from creating the model at the starting point. So now you have your model created, but it's just a model. And you're wondering probably at this point, well, how does it know that it's supposed to read those same files that I uploaded in Google Cloud Storage? Well, actually, all you've done here really is just set the name of the model that you want to deploy, but you haven't really defined the guts of that model yet. Define that guts actually is, in GCP at least, is called creating a version. Creating a version is, as it's declared, you're basically declaring exactly what conditions you built your local machine learning model in, such as the Python version, the machine learning framework, as well as the version for that framework as well. So in our current context, we built our TensorFlow model using TensorFlow 2.7 and in Python 3.7. And again, you do the basic naming schema, you give it a name, in this case, very simplistic, version 1, and the description is just, oh, this is version 1 of the AI code talk text classifier. TensorFlow specifically is Google owned. It's Google's own open source machine learning framework. So using the pre-built container approach in this case is perfectly fine. They have a lot of inference being done under the hood to ensure that your machine learning model is going to be deployed as expected, just like in your local environment. So there isn't really much needed to be done there. The custom container approach, of course, as you noticed, is in the preview mode, and that's essentially one of the beta tools that they've been propagating over time and testing before they actually wanted to be built up into production. So if you're looking to really get your model out as soon as possible, I would advise not to necessarily go and try out those preview sections yet. More so if you're more so just trying to lay the grounds and see exactly how things work in the cloud space, more so you'd want to tackle that environment. So you got your configuration set up. What else do you need to do with your model? Well, you can configure how the model will scale to your workload. Now, this is a huge benefit of being in the cloud environment because basically, once you have your model deployed, you make the cloud platform determine exactly how you want your model to scale. In very crowded scenarios where thousands of people will be hitting your model and asking it for a prediction, you might want 1,000 replicas of that same model to be created immediately once it starts noticing that. Google, Amazon, as well as Microsoft all have those auto-scaling monitoring tools to make sure that every user who's contacting your model gets the most responsive behavior as soon as possible. And it does so by scaling up instances. So here you'll notice that for auto scaling, we set a minimum instance of 1. So that always means that no matter what happens, there's always going to be one replica of our model deployed somewhere in the cloud. And as we need more models, Google will detect that and scale and add more as it needs. And then after you determine your auto scaling, you then configure the machine type as well as your GPU. So again, before you, from taking notes of the benchmarking of your model locally, you can infer if you need to attach a GPU or if you don't, or maybe you just need a typical machine with just a few vCPUs. If you do attach a GPU, expect a lot of additional costs because GPU by itself in hardware is a pretty pricey product, and they do charge hourly on how often you be attaching that GPU to your model. But yeah, once you have all these configured, you just assign the directory to where your machine learning model is hosted, and you are ready to go. It takes a few minutes for it to actually read and process your machine learning model. But at a point, you'll notice that, especially in this example, we have our code talks text model properly deployed with the default version being the version we just assigned, with the typical description and, of course, the endpoint where it is located in the world. So in this case, it's located in US Central 1. So whenever you're interfacing with it, you have to be aware of the region that your model is located in. So now we have your model deployed, and now you want to make your predictions. But how exactly? Well, there's two main approaches that I want to tackle today. The first being Java. So in this bottom scenario here, the idea is that you have your client, which is maybe like a front-end application that just wants to immediately talk to the AI model you have hosted online. You use a simple JavaScript call to that model, and you're good to go. You get that prediction, and it's sent back to you on the client side. And for the top approach, we have a function middleware built in Python that takes in the input of the client and feeds it back to the model, and then from there, it transfers it back to the function middleware and then back to the client. Both of these approaches are viable. For this particular demo, I'm going to be going with the topmost approach because here at Call Simulator, that's how we mainly design our pipelines. And the main benefit for that is because no matter what the client is on the user side, no matter what service or client it is, you can always just call the same function middleware and contact your model regardless of framework or compatibility issues. So it allows for both your users and your developers to interface with your model, as well as your outside external clients to also interact with it whenever possible. So getting predictions the Python way. So this is one of 3 slides that are very code heavy. I try not to make a lot of these slides code heavy because I wasn't really sure how everyone sat regarding coding in Python. So I kind of just made a list on the right-hand side of the main points of this code block. This is verbatim in the documentation on Google Cloud's own AI prediction documents. And so this is highly and readily available at any point in time online easily. But going down the list, from step 1, basically define the API service that you're going to be interfacing with. In this case, it's going to be the discovery build model, which is the machine learning API. Number 2 is you define the function that will be calling the model to gain a prediction on. Number 3 is this name block right here, where you define the location of the model, where essentially it's just the name of your model and the project, the Google Cloud project that you use to host that model in. And then number 4 is you're actually making a prediction towards that model given a block of instances, and we'll talk about the instances in a few slides. But basically, you're just sending the input that you want to that model, and then step 5 is you get a prediction back from it. And in that prediction, you'll see exactly, what your input is classified as based on the model's exact task that needs to be done. So, as mentioned in this slide here, we want to have some kind of function middleware that will take in the input, process it, and then feed it to the actual model deployed in the cloud. And the method that we'll use here is a very simple one. It's also a tool in Google Cloud called Google Cloud Functions. This is a very, very simple service, but although simple, very powerful. Basically, Cloud Functions are serverless, meaning that they can scale from 0 to 1,000 to 3,000 instances, depending on how many people are actually calling it around the world or wherever it may be. So Google Cloud, of course, keeps track of how much traffic is being allocated to these functions and scales them up as need be. Specifically for this case, we're going to be using it as an input function to intake user request data, as well as to feed that data into the machine learning model. So at the bottom here is the second slide of just basic code. This is the guts of the Google Cloud function. Essentially, it takes in an input key, which will explain how that is being sent across, formats it into the proper instances format to be fed into the machine learning model, and then it gets a prediction from it and it just outputs it and spits it back out to the client. And from there, it's up to the client to decide what they want to do with it. So let's actually get into an example to kind of get a better idea of this. So the first example here is going to be text classification. So we built a very simple model from the IMDb sentiment classification data set. Basically what this data set is a group of raw text strings of both positive and negative movie reviews. And essentially what we've done after training it is that this model can now categorize any string that's given to it based on the words in that string. So at the bottom here, we have a basic data flow diagram of the inputs and outputs of each service. From the client side, they're going to be sending in a string of, a movie review. Is this movie good? This movie is terrible. This movie is so and so, and it's being fed into this cloud function. This cloud function takes that input, formats it in the proper way that should be intaked into the model, and then from there, the model makes a prediction and feeds that back out in the probability array from 0 to 1 back to the client. And from that probability array, the client can decide how they want to display that. Either say, okay, well, we categorize your model as being, we categorize your view as being very positive, or your review as being very negative. So here's an example. Actually, this is using Postman, which is a tool for testing your own applications and APIs. The URL up here is actually hosted right now online. So if anyone is actually wanting to interface with it, you can actually make a post request to this particular URL and simply give a key, which is the input, and the value, which is your string or your review of a certain movie, and it'll output you a probability array of the prediction that the model that we have deployed made. So for a basic idea, values closer to 0 means that it predicted that it was a negative review, and values closer to 1 indicate that it was a positive review. So for the first example, I basically just wrote, this movie is terrible. And as expected, the text classifier model gave me a 0.005, meaning that it expected that that was a very negative review, which lines up exactly as we expected. And then for the second example, I just said, this movie is amazing. And I got a value very, very close to 1, pretty much 1, saying that, okay, this review is very positive, or it is positive based on this classification. And that's basically a very simple example of deploying your model into the cloud, getting predictions, and seeing exactly what's being outputted and making sure that it's consistent with how you've had it deployed locally. And of course, this is just using text and with a very simple binary classifier, right? It's either 0 if it's bad or 1 if it's good. So I'd like to present another example with a more complicated sort of data set. Now we're going to be classifying images of hands. So on this data set that we trained on is about 3,000 images of CGI generated hands that represent the gestures rock, paper, or scissors. So again, we split this data set into like 2/3 being training data sets and 1/3 being evaluation sets. And we feed it into our TensorFlow algorithm, and it creates a model that predicts if a hand image given is rock, paper, or scissors. So we basically did the same process before. We uploaded this model's contents to the Google Cloud bucket. We deployed it on AI platform. We created a cloud function to intake that data, and we do some testing and see if it works. And here's an example of that data flow diagram. Instead of just passing in a string that says, as before, if this review was good or not, we're actually taking in links to images online. So you can send in any link to any Google image of a hand, whether it be doing any sort of gesture online. And what the cloud function will do is intake that image, formats it into the proper data format, and feeds it back into the model to gain predictions about it. And here's a little bit more detail. This is the last large code block here regarding that. But basically, for this cloud function, it's a little bit more complicated because now we're actually downloading images into memory and converting it into the proper format to be fed into the model. So starting from point 1, the user just gives a link to a random hand located somewhere on the internet. Then the cloud function downloads that and converts it to a 300 by 300 image. Mainly because that's the data set that it was trained on. All the images were 300 by 300, so you have to make it consistent with the data that you trained it on, or else there could be some inconsistencies when you're making your predictions. Then we convert that image data to an encoded string, and then we feed that back into the AI platform hosted model. And at the end, you get your probability array as before, but this time it's a little bit different because now there's three labels: rock, paper, and scissors. And likewise, using Postman, we give a simple example. On the left-hand side, you'll notice that for the key, we give an image path, and it's the link to some random image of a hand online. This hand is, probably giving a high five, but in the context of the model, it's giving the paper gesture, right? And so you'll notice that the probability array we get at the bottom here is basically corresponding to each label. The first one being rock, second one being paper, the third one being scissors. So you'll notice that the one that's classifying for scissors here is very close to one, meaning that model predicted that image to be more than likely paper, the paper gesture. That's a very simple image classifier, again, hosted in the cloud environment and easy for you to get inference of and see exactly how it's performing just by making simple browser requests to that cloud function. And this is pretty much how working in the cloud ML focused services is like. It's very easy and intuitive to get your platform set up, and you just need to do a little bit of configuring on how you want to get your data to be fed into your model to actually get it, to make predictions and to get you your proper outputs. But even so, there's still some pros and cons you got to think about when using these services. Particularly, I'll just go through the list of pros and cons right now. For GCP specifically, or other managed platforms, once you have your model up in Google Cloud or AWS or Azure, it's all being managed by the cloud platform. So once it's up there, you can access it whenever you want and however you want, so long as you have the entry point to do so. They also provide a lot of built-in logging tools for debugging and gaining performance metrics for your model if you ever want to, go back and refine the logic of it, or you want to optimize some things. And of course, having that customizable machine and GPU allows for a lot of variability in cost as well as speed and responsiveness. But there are some cons that come along with this. You are using AI platform, and basically machine learning in general isn't cheap. You definitely are paying a premium when you have it hosted in these specific machine learning environments, regardless of the size or complexity of your model. So always keep that in mind. Of course, you could always customize the machine, remove the GPU if you'd like, but even so, it's still a little bit more pricey than other alternatives. So always keep that in mind. Again, you have to also abide by those Google or Microsoft or Amazon ways of obtaining a prediction within those certain environments. We sort of alleviated that here by making a cloud function that does it for us, but it can become cumbersome if for some reason during your own development you need to move between different cloud platforms, as now you need to switch to Microsoft's way of obtaining prediction, and then eventually Amazon's, and it could just become a little inconvenient. And lastly, for those people who want to be more on hands with their model, or who really want to have the best say of their model, once you have your model deployed in these specific ML services, you're really giving up a lot of the control of your model to the platform. And depending on what developer you are, that might be a pro for you or that might be a con for you. But regardless, you have to keep that into account. And of course, you also have to think that, as mentioned before, some frameworks that you work in might not be compatible with these ML services as of yet. And so you do hit an obstacle when you deploy, for example, something in PyTorch until as of recently. But you could still hit that blockade. And the question now is, how exactly do you deal with that blockade? Well, there are some alternative services online in the cloud space that you can use that aren't necessarily designed for machine learning, but they can be used nonetheless to at least get your product out there, your AI out there and start interfacing with other applications just to get the development process starting. I kind of listed these in order of complexity, with the first one being the easiest to approach, and the third being the most complicated for like the most dedicated developers, honestly. Um, and all of these have a major trend amongst themselves, which is the idea of containers and controlled environments. Um, so I'm going to go over briefly about containers and Docker and containerizing applications. Again, if we wanted to go a little bit more deeper into this, this could become its entire own code talk in itself, because the vastness of containerized environments is so customizable to the user that you can go on and on about the intricacies of it. But basically, a containerized environment is just a platform that you, as a developer, can use to bundle your code however you like it. You can have it with your own operating system, with your own environment variables and dependencies, and you can even load your own model regardless of framework in that Docker container. And as long as you have that working in itself as a container, and you have it hosted on the cloud platform, as long as you have the proper resources allocated to it, the cloud platform won't ask any questions on how that container is running or what is in that container. As long as it can run, it will just host that service. So this is kind of like a trick to get past the compatibility requirements that you might meet if you're working in a strange framework, machine learning framework that isn't currently supported. So when you have your Docker container, you usually build it locally, similarly to how you build your machine learning models. And similarly, how we uploaded our machine learning model files to a Google Cloud Storage bucket, there are also services on the cloud where you'll store your containers. In Google Cloud, there's specifically the container registry, and it's very similar to the Cloud Storage bucket, but instead of blobs of files, like the model files, for example, you have just container images in there. And what you can do here is you can tag your images, as well as keep track of it for other developers to download and run their applications on as well. This is very convenient, especially if you deal with like a lot of compatibility issues in your development environment, because all your peers will need to do in this case is just download that image and run it locally, and it's essentially them working on your current environment that you built this application on. So very convenient and a powerful tool. But now you have those containers set up, we can go into some of the services that will use those containers. So Cloud Run is one of those services. You can think of Cloud Run basically as a cloud function, but instead of a snippet of code, it's just a container in itself. And this is really attractive for developers because it allows you to still have control of the environment that you have your application hosted in, as well as being able to customize the amount of memory you allocate to it, the number of virtual CPUs, and how it will scale depending on the workload of your application. So again, if you only want you and your peers to be invoking it, you can set a maximum of like 3 instances. Or if you're expecting the whole world to be interacting with your application, you can set it to 3,000 instances. And regardless of that, it will scale accordingly, given that your container is adequately built to scale that fast. And it's convenient too because the cloud platform handles it all for you. You can, once you have this Cloud Run container deployed, you can sit back and relax. And of course, if anything happens, the platform will notify you of any problems, but more than likely so, it will scale up and down as you see fit. And you just have to focus on developing and iterating on your application itself. So this is definitely the simplest alternative approach if you don't find that the ML solutions satisfy your needs. And here's a data flow diagram for just Cloud Run. As you see, from the client side, you basically just send the data that you want the model to predict. And within that Cloud Run instance, you have everything packaged in there. You have the model, the logic to transform the data into the right format, and how it's going to be sent back to the user. And you might be thinking, okay, well, this is a lot simpler than setting up a cloud function and routing it to AI platform. So why not just do this all the time rather than having it hosted in, Cloud ML services? Well, again, this goes back to Cloud Run not necessarily being for machine learning, but more so just being for containerized applications. So although you do have a lot more control in this environment, you are giving up GPU support, which is very detrimental if you have a huge model that's like 2 GB big and that takes a long time to spin up. Essentially, the idea is the larger your container is and the more complex it is, the longer it takes to spin up and start scaling. So for applications where there are thousands of users talking to it, you may have certain cases where 800 of those 1,000 users are just stuck there waiting because this container is just taking 1 to 2 minutes to just spin up another one for it to begin making more predictions, which is not ideal in a production environment. So again, while this is very convenient, containerized environments are very convenient and customizable, they do have a trade-off where you aren't getting the necessary configurations for more complex models. And still going off of containerized environments, another service that you can use is Compute Engine. And what Compute Engine basically does is it hosts virtual machines. You can think of a virtual machine as your laptop, your computer. It's basically your local computer hosted in the cloud with all the bells and whistles. Not only can it host like the just machine configuration itself, it can also host specific Docker containers. The caveat here is that you are paying for the uptime of that instance at all times. This is nice for developers who want to have more manual control of their services, but again, if you're in a scenario where you accidentally leave your service online over the weekend with 2 GPUs attached to it, coming back on Monday morning, you might see a lot of expenses that you did not expect just by leaving one of these services up and running. So you do need to maybe configure additional services around these virtual machines to make sure that they spin up and spin down during certain times of the day when you're not expecting a lot of people or anyone to be interfacing with your machine learning application. In this certain case as well, you'll be usually calling that compute engine instance by using a load balancer. It's basically just a way to route that same request data from your client to that compute engine in a secure way. And like the AI platform, you can attach GPUs to this instance, but you will need to also do some manual driver installation and testing to make sure that it recognizes that the GPU is attached and then the purpose for it is to do model predictions. So again, it's really convenient, but it is a lot more hands-on and complicated. And it can be complicated to some users beginning to work in that space. And then lastly, we have the great beast itself, the Kubernetes Engine. Now, again, this can become its own entire code talk because Kubernetes is widely customizable, and the people who are really deep in it can go on and on about the intricacies of it. But basically, in a nutshell, a Kubernetes cluster is basically a bunch of machines all together within this environment, with one or several of those machines being the host or the brains of the whole application. And what the user does is that they govern exactly how those host machines will be allocating resources to the machine learning models or the other front-end, back-end applications that interact with the machine learning model, and how those resources will scale up and down depending on the traffic that it sees on a day-to-day basis. This is the barest metal that you can basically get to on the cloud platform, and it can be very difficult and cumbersome to set up. So it more so is a whole venture in itself to get acquainted with this kind of system. But in the long run, if you do end up successfully doing this, you can actually alleviate a lot of the costs that you might be missing out on, that you might be accumulating if you were hosting this model and these services in a different environment. But it also has a trade-off. If you mismanage it, you will be propagating a lot of additional costs as an expense. So personally, I wouldn't advise this approach if you're beginning in the ML space, but if you do feel adventurous and you want to take this approach, I would suggest setting up your Kubernetes cluster locally before you end up actually deploying it to the cloud space. And so I've gone over 3 of the main alternatives that at least I would interface with, as well as how we look at things at Cost Simulator and USI for machine learning deployment. And I'd like to just leave off on some certain tips and considerations if you're still curious about this containerized approach to machine learning. The first one being, rather than having the machine model in your container, download it instead, or you might want to take the option of downloading it instead from cloud storage and loading it in memory on the startup. This makes the container itself a lot lighter and allows for you to spin up that instance a lot sooner for your customers or your users to at least get predictions in a faster way. The second notion is in serverless approaches like Cloud Run, or the first alternative approach that we mentioned, memory in this case is considering both the RAM and the disk storage. And that isn't ideal in certain development environments, because if you're testing your model locally and you're like, okay, my model takes up 6 gigs of RAM, but my model also by itself takes up 2 gigs of storage. When you deploy it on Cloud Run, you'll notice that the amount of memory it actually takes up is 8 gigs of memory. So you need to do the math to outweigh those costs when you're deploying it in such an environment like that. And lastly, if you're expecting a lot of consistent usage or just some minimal consistent usage and you're unsure of how responsive your application is, it's always good to just keep a minimum instance of one of your Cloud Run instance always running. So it ensures that no matter what happens or who invokes it, there's always going to be one of those models out there listening in and ready to receive the call at any given notice. So at the end of this, I'd like to give a quick recap on some of the main things that you should be getting out of this talk. The first one being benchmark your models at any point in time you can. Keep track of the bottlenecks of your models as well. This is super, super important. It'll save you a lot of tedium in the long run, and and it'll also help you optimize your model once more tasks and you get more data as well to iterate on that. Number 2 is if you're new and you're starting in the cloud space and you want to start just jumping into machine learning, using the cloud ML services are a very good starting point to start from. There really isn't much to say here because we kind of went over those 2 examples and they were very simple just by using the interface and using the tools that the cloud service provided. Third one is if you don't like the cloud ML approach, containers, again, are very customizable. And if you have a framework that doesn't necessarily work that well in those services, you should always be looking to containers to see how it fits there. And even if you're not expecting to use containers, it's always good practice to containerize your applications regardless, because you'll never know when you need to transfer it or send that model to other people in the world or right next door. Number 4 is always make sure to balance the cost of your application with the user responsiveness. Now, this is more of like a business perspective, but as you develop your model and your application, this will be an ongoing topic that you keep in the back of your mind. Because honestly, hosting machine learning models isn't cheap, especially when you have attached GPUs. They can definitely run up the costs very quickly and unexpectedly if you're not constantly keeping monitor of that. So number 4 is very important in that regard. And the last point is experiment. As I said before, a lot of these cloud platforms now provide catalogs for you to explore the different models that different industries have been developing and deploying for you to play with and for you to see exactly how they have built their applications. So even if you're sort of intimidated and overwhelmed by the machine learning space in the cloud, there's always outlets for you to just get things running and get things out there and test it yourself and see how it works. And with that, I believe that's the end of my talk. So I'd like to just say thank you for listening. And also I'd like to thank Domi Station for encouraging these kind of open-ended discussions and having people from Tallahassee discuss just from their point of view exactly how they go about developing these applications and just being open to these kinds of discussions in general. And of course, I'd like to thank David Lawson and USci for giving me this opportunity to give this presentation and talk about my work throughout my years working in the cloud networking space. And once again, I'd like to thank you for those listening online to my talk and just me rambling on about machine learning models and how to deploy them online. But I think that's it. So if there's any questions, like,
I have a question.
Sure.
How do you go about choosing your cloud platform? Like I know you mentioned like AWS and Google Cloud.
Yeah. So I'll tell you from our example. Our example with Google Cloud is that we had a very good initial business deal with GCP. They were very generous to give us like good quotas and a lot of credits to get started. Honestly, personally, in the long run, it really just depends on how your organization interacts on what they choose to use as their cloud platform. Personally, I think in the long run it doesn't really matter. They kind of all do the same thing. It's just up to how you feel about that cloud platform and what deals they kind of give you. In the end goal, it's all the same. If you have a model built in a specific framework that isn't supported, maybe you want to look at one platform over the other. But nowadays, it's so competitive that when one platform makes an improvement or improvises, the other ones follow suit very soon. So it's very competitive in that space. So yeah. And if you sign up for any of them, you get $300 in credits to play around with for like 3 months. So like you can always like mix and match if you just want to do some free stuff.
And then I had a second question. Can you explain GPU?
So a GPU is a graphic processing unit. It's not your CPU. Your CPU is like just does all the reading and writing instructions from memory to your motherboard, essentially. A GPU handles video rendering. It's essentially a whole other component that just does video rendering, batching, and input and output for machine learning development. For video gaming terms, it's what renders the graphics for you, or in crypto terms, it's what does the mining for you. I don't know if you've seen those crypto like environments where like they have literally batches and batches of these big shelves of just GPUs just spinning and running and running. They're highly valuable in computation, and it's the optimal way to train your models because you can easily batch images together and just feed them through your network to train it over and over and over again. The machine learning training process is a lot of repetition. So you want to, and it's faster when you batch them together. So if I'm training a model that classifies like animals, right? Let's say there's it's a simple classifier between cats, dogs, and horses. I have 3,000 images of cats, 3,000 images of dogs, 3,000 images of horses. With a GPU, I can batch 1,000. This kind of hyperbolic, right? But I can batch 1,000 images of cats and just feed them all at once into the model in one go. And the GPU is able to, capture all of that together in a nice like compartmentalized way and just feed it into the network without it, needing to stop. As opposed to CPU, where maybe it has to go through each image, process it, and then feed it into the network and whatnot. Because in most cases, your CPU is doing other things like making sure that your operating system is running, keeping track of your other components in your computer and whatnot. The GPU is just handling the running of the training in general.
Okay. So it's not required. You can do GPU or CPU.
Mm-hmm.
Okay.
Yeah, if you're really tight on the budget, you can just do everything off CPU, and it should just work. It really should. Yeah. But a lot of people use GPUs for images mainly, because images are, they're just huge pixel boxes. Yeah.
And then, like, what advice would you give for like someone like starting out, like someone who wants to get to like applying machine learning or AI to their software applications? Like, how would they get started?
So I would definitely say if you're looking at it from the cloud approach, definitely depending on the cloud platform that you choose, should go to the machine learning centric services of that cloud platform. So if you're in Google Cloud, you go to the AI platform. If you're in Microsoft, you go to the Machine Learning Studio. And if you're in Amazon Web Services, you go to SageMaker Studio. And whether or not you develop a model yourself, you can always look at example models that they expose to you. So there's actually catalogs now where you can look at different models that other industries have developed, and they just share to the world to see, and you can actually deploy them in your own environment, see what inputs they take, see what the purpose is of that model, and then kind of get an idea of at least how that process starts. But if you're talking about machine learning development, I would just say look at Andrew Ng's class on machine learning development. I think it's widely known about that class, right? But that's more so just getting the concepts of it. But I know for some people, they more so want just like a visual representation. I want to see results now, and at least like get. I know a lot of people like to learn by seeing the end product first and then working back on that, rather than starting from scratch and being like, okay, well, here's what a tensor is, and here's what your machine learning model looks like, and you're like, okay, well, I don't know what this means, but if you see the end product, you kind of reverse engineer it and maybe find a starting point to go off of. So yeah, there's definitely different approaches you can do.
Thank you.
Yeah.